contacted him on Great Lakes ships, which was a lot of fun as he was going through the locks and all of that. So that was great. So Ron, did you think?
Our topic tonight is inductors and capacitors. Are inductors and capacitors important to radio? Very important. Can I have you scroll, please? Now, there are two types of current, and I suspect you've already learned this: direct current and alternating current. Direct current, it flows in only one direction, so it's always going this way. But AC is kind of like me; I never know which way I'm going, so it's back and forth. Now, if you look at a wave diagram of AC, looks something like this, okay? This is voltage, this is time. Our power in the city is 60 cycle, which means 60 times a second it's going to go through one of those complete cycles. Or 120 times a second it's going to change direction. This is important. DC is a flat line, right? It's just a straight line. And DC always flows in one way. Okay, listen. Oh, we have these. I don't have to draw. Okay, next one. And there's the AC, time and voltage. Okay, yeah. In any conductor, any wire where there's current flowing and it's flowing in one direction, there's a magnetic field, okay, around that wire. And that magnetic field is created by the motion of the electrons through the wire. The other thing is a magnetic field also tries to stop the current, okay? So it works, the magnetic field. I got brain damage, so I will skip on my words sometimes, okay? The magnetic field is created by the moving electrons, but that magnetic field is also going to repulse the electrons, going to make it hard for them to go. So an inductor is, okay, an inductor is a coil of wire. So if we take wire and we coil it up, it becomes an inductor. Now, this inductor will have current flowing through it, and each of those magnetic fields will add to each other so that it becomes stronger and stronger as the amount of current goes through it. More current, stronger the field. There's more number of turns, stronger the field. However, the current and when we put DC through here, this can be used as an electromagnet, right? So it will pick stuff up. We normally have some kind of a core in here, usually iron or, and there are other materials that we use in electronics that we will talk about later, but the iron core makes the magnetic field stronger because it can handle the magnetism, whereas air, it has no physical quality to handle that. Now, this is fine with direct current. When direct current goes through it, there's no problem. But when we start going back and forth, so we start going with AC and we start going this way, then this way, then this way, then this way, we're going to end up with a little bit of a problem. And one of the problems is the current. The current will be what is called, went too far, be out of phase. Current is usually 90 degrees out of phase with, it's not very accurate, but so the current will be behind the voltage. The voltage is instantaneous, the current is behind. always in an inductive situation. In the book it says, it talks about the voltage being leading the current, but don't do that. It's the current lags the voltage. And it's very important to do it that way because capacitors are the exact opposite. This lag introduces a timing factor into this, okay, which is very important as we get into the farther into inductors. So, various unshielded inductors. Unshielded. Why do they call it unshielded?
Just because they're unshielded?
Yeah, I guess. This is a toroid. I have a toroid here too, but it doesn't matter. It's wound around in a circle, so it doesn't have to have magnetic shielding in a circuit. It doesn't really explain to you why, though. Anyway, there's different types of inductors. This is a toroid type of inductor. This is just a regular inductor. This is called an iron core, air core. You notice the two lines? That's for the iron core. Sorry, I'm not looking at you. That's for the iron core, and this is for the air core. The Air Corps, U.S. Air Force. This is an air core inductor. This is an antenna inductor. This is used on an antenna to balance, to make the antenna appear longer, which is later in your lessons. You'll learn about that. Okay, inductance is measured in henries. A henry is a measure of an intensity of a magnetic field, but a henry is a rather large guy. We don't use a whole henry, but we usually use millihenries, microhenries, and I don't think we use picohenries in this, but we do use millihenries and microhenries. Millihenry is a thousandth of a henry. Well, there's your scales there, but those are interesting. The way we usually say is 10 to the third, 10 to the 6th, 10 to the 12th. And then when we get into the other way, no, these are 10 to the minus 12 rather, 10 to the minus 6, 10 to the minus 3. If you know about exponents. Okay. Okay, then the amount of inductance is influenced by a number of factors. Yes, the spacing between the turns, the diameter of the coil, the number of coil turns, size of the wire used, type of materials inside the coil. All of these are factors. That's a powdered core, iron core for higher inductance. The highest is soft iron core. Small diameter, larger diameter, wide spacing, close spacing. All that's straightforward. Sure.
A brief question about the core. I know that in for instance, in FPV, for long distance antennas for FPV, for flying drones and
Yep,
videos,
yep, I know what you mean.
There's sometimes a solid plastic core. Does that have any effect to the weight at all, or is it because
It's a noise kill. It's to kill noise.
Oh, okay.
It's we get into it when we start talking about inductance. Right now, just inductors. This is a very tiny one, but it has a screw or whatever in there, and you can move the core in or out. By moving the core in or out, you change the inductance, and that's very important later on. So we can change the value of this. It's an important thing. Ouch. Okay, next, please. When a DC current is first applied, the increasing magnetic field opposes current flow. Right, exactly what I said. So as the current is trying to get in there, that counter EMF, oh, there's a new word. So electromotive force is the applied force. The counter EMF is the created force. And it is in an opposite direction to that which is applying it. And that's created by the movement of the electrons through the coil. Because the coil will generate a magnetic field. The magnetic field opposes the movement because the magnetic field is backwards.
Can you repeat those two?
Okay. EMF, or electromotive force.
Motor force?
Motive.
Motive, okay.
Motive force is the force that pushes the electrons. We can talk about that after too, but that's the basic concept that you need, that it's pushing electrons. And it's having a hard time getting through that coil of wire because of the counter EMF, counter electromotive force, which is also very important to understand. The magnetic field begins to collapse and there's a rush of current in the other direction. Sometimes they're very, okay. So when you have a coil and you energize it with DC and you remove the DC, that current has, if it's connected, that without being connected to the source, but if you connect both wires together, there's an enormous amount of current goes through there because that field is collapsing, and as that field is collapsing, it's creating, because it's a magnet that's cutting a conductor. Anytime a magnetic field cuts a conductor, whether it's because the magnetic field is increasing or decreasing, or because it's moving across the conductor, it's creating energy. Okay, sometimes that's a hard concept to understand. If you have questions, please interrupt me, because this stuff to me is second nature, but I know it's not to those who are starting out. Okay. Okay, now when AC is applied to an inductor, this one is when it becomes interesting. During the first half of the cycle, the magnetic field builds as if it were a DC current. Obviously, it's going to build up. During the next half of the cycle, the current is reversed, which is exactly right. It's going to go the other direction. But that lag that we talked about is there. It resists the motion, but it does go to maximum. But it goes to maximum out of phase. And the problem here is this is the only power in that circuit. There's no power here or here. Why? Well, that's hard to explain. So when you calculate power in an AC circuit, it's a little different calculation. You have to know what your percentage of lag, what your percentage of leading is, and all that. That way beyond our scope here, but just be aware. So they can work against each other, resulting in a lower current flow. That's true. Next, please. Okay, so if we have two inductors in series, we can simply add the henries together. Okay, L is for inductance. Always. Why is it an L? I don't know. I know why it's a Henry, because of some guy named Henry. Henry, I forget.
Henry L?
Huh?
Henry L?
Yeah, it could be.
Well,
that's Louis.
oh. I was already taken by current, so I had to do something else, right?
Yeah, it could be. Anyway, this is how we determine the total inductance in a series circuit. Next, please. This is the parallel circuit. You are familiar with series and parallel, right? That's understood. Okay. Now I have three of them in parallel. Well, I'm losing inductance now, and the inductance will be smaller than the smallest inductor. So we're going to do the inverse ratio. So the total, 1 over the total is equal to 1 over each one of them added together, and then you flip it up, and then you got your answer for L, for the circuit, okay? Is that clear? Does anybody have a problem with that? That's the same as your parallel circuit for resistance, right? Okay, let's try the next one, see if it is. Because the magnetic field across the inductor. Oh yeah, this is where it gets interesting. So I have a magnetic field in one coil, and I have another coil over here. Well, I'm going to have, I think I put this coil here, and I put this coil there. Now this one has a current going through it. Now this one will have a current too, because that magnetic field will influence the coil, the wires. Because every time a magnetic field cuts across a wire, it creates energy, it creates a flow. Anytime. And it doesn't matter whether that magnetic field is being moved or just the current. The current will create the field, and the field will expand and contract because it's AC, right? The polarity will change back and forth. So this is north, that's north. This is north, that's north. 120 times a second it'll change direction. So that will create an AC current in the second coil.
Because one cycle is 60, we do 60,
Yeah.
so it's double that, right?
Well, it's positive, then it's negative. Okay?
Right.
Okay, so half the time it's positive, half the time it's negative.
Yeah.
So it's 120 times a second it's changing.
Now, an example of magnetic field, would that be like induction?
Yeah,
So like my phone, I can charge it through induction?
inductor, yes. It's the same idea.
Okay, all right.
You're putting it next to a magnetic field. That magnetic field is,
Charging.
but we're controlling the magnetic field by, in that instance, to produce a voltage that you need.
It charges that.
Okay,
Okay.
and you're. Okay, this is the basis of transformers. They're not those little things that change from one thing to another. But they actually are changing. They're changing voltage to a different voltage, current to a different current. Okay, can I have the next one, please? So this is an example of a transformer. Transformer has two sides: primary side, secondary side. Primary side is a side to which you attach the source, or the source. That's the side you're powering. What you're getting out to this side is the result of that relationship. Okay, so we have a certain current here, and the iron core magnetic field, this field is changing direction back and forth. It's creating an AC current in this side. And as the current flows, the voltage is created. The voltage is created across this load. Right? We always measure across something. That's because there is no voltage with an open wire. There's no voltage. Essentially. There is, but it's another topic. But the voltage will drop across here, and it'll be the entire voltage in this circuit because it's resistance. So this is the relationship between power in and power out. The number of turns in the source over the number of turns in the primary is directly related to the voltage in the secondary over the voltage in the primary. NS over NP equals turns ratio. So if I have a transformer with 100 turns on one side and 10 turns on the other side, I will have 100 volts, and I put 100 volts on or 1 volt on the primary, then I'll have a 100 to 1. I can't put numbers anymore. I have a turns ratio of 100 to 10 or 10 to 1. So if I put 100 volts on the input, I'm going to get 10 volts on the output because I have less turns. But the current on the input is power in equals power out. So 100 volts, say 1 amp, so I have a power of 100 watts. So on the other side of the transformer, I'm going to have 100 watts. So I only have 10 volts. So how much current do I have? E over IR. You don't need to know the resistance. The ratio is 10 to 1. So if I have 10 volts, then I have to have 10 amps to make 100 watts. So that's one of the things about transformers. They can go the other way.
Step down or step up.
Yeah, you can have a step-up transformer or a step-down transformer. Step-up transformer would have 10 wires on 10 turns on the primary and 100 turns on the secondary. So that I put 10 volts in here, I get 100 volts out there. But again, I only get 1 amp, and I got to use 10 amps to get that 1 amp.
Okay.
That makes sense? Transformers are important because we use them for all kinds of things. We use them because we have 110 volts coming out of the wall, and we only need 13.8 volts for our radios. So we use a transformer to reduce that, and then we convert that AC to DC using diodes and whatever other fancy things we use. But the transformer is essential. Next, please. Okay, we did this. If number of seconds, this is a step up and this is a step down. That's in your notes anyway. Next. Ability to hold a charge. Oh, now we're into capacitors. Well, we haven't left inductor. Oh, the way he did it in here and the way it's done here is different, but that's okay. We'll do it this way. A capacitor has capacity. The best way to remember it. It holds a charge. It has two plates, or two poles, whatever you want to call them, but they're plates. In between can be air, or it can be some material. Okay, so what happens here is if I put a DC on here, and I put a negative charge on this side, there's no connection between here and there. So that DC can't go through there. But what it does do is push all the electrons away from here to give you a balance. So you will now have a positive side and a negative side. Because, so, if you were to remove the source, that will stay. That charge will stay. And you take the ends of the capacitor and put them together, you're going to get a spark because it'll discharge and seek equilibrium. This is how electricity actually works. It works to find equilibrium, always. So the reason we have electron flow is because I got too many electrons here, I don't have enough over there. So if you keep going continuously, it'll balance out, and then you have zero, you have no current. Okay. Physical construction. Okay, these are different types. This is a mica, those are ceramics, cylindrical. This is how they're constructed. But I want to show you one, and I want to make you understand this one before I go any further. Most capacitors don't matter how you hook them up. But these guys are bombs, and they can explode. They will point to the negative lead, the negative lead. You must hook them up in the circuit properly. If you don't, they can explode. And believe me, when they explode, that's a lot of energy that's encapsulated in this little tin gizmo. They will go through this ceiling, the plastic ceiling. I've seen it go.
What kind of capacitors are those?
Those are called electrolytic. So anytime you come across an electrolytic capacitor, be very careful to get your polarities correct. You've seen them go. Okay, amount of capacitors are rated by the amount of charge that can be held, the voltage handling capabilities, and insulating material between the plates.
Ron,
Yeah.
you're saying about the electrolytic capacitors. Think of them as a big battery.
Yeah.
Okay, that's
Exactly.
basically what that is. And the thing is, if a battery gets goes hook it up, you're trying to charge it the wrong way, it'll heat up and blow.
Yeah.
And it's the same idea.
The only problem I have, you're right. The only problem I have with calling them like batteries is batteries do not store electricity. Batteries are an electrochemical activity. So they create energy through electrochemical action, but they don't store electricity. The only thing that actually stores electricity is a capacitor, or an inductor in a sense, because it stores the magnetic field, which can create the current, right? These round capacitors are rolled. They have paper between the thin sheets of tin foil. The paper is sometimes wax paper, or now with all kinds of materials, mylar, there's, excuse me, etc. And then you can see the same idea here. That's a tantalum pentoxide dielectric. We'll talk about dielectric in a minute. Manganese dioxide, solid electrolyte. Chipped epoxy, tantalum, negatively blind, etc. Oh yeah, these can be negative and positive as well because they're electrolytic. See, so they're tantalum, but they're electrolytic. Watch for that word. Okay, let's go for the next one. Unit of capacitance is the farad, but the farad is like a 1 farad capacitor, humongous. I don't even think it fit it in here. So they're really big. So we use the micro, the nano, and the pico. 10 to the minus 6, 10 to the minus 9, 10 to the minus 12. 3 physical factors affecting capacitance values: plate spacing, how far they're spaced apart; plate surface area, how big the plate is. That's why we roll up that tin foil. So we got, you got some length like this, and it's in that little wee package. And the dielectric material. The dielectric is the thing that is between the plates. Okay, the dielectric is something that won't pass electricity, but it will pass magnetism.
Like what?
Like what kind of stuff?
Yeah.
Oh, glass
Okay.
is a good dielectric.
Ceramic.
Ceramics, yeah. The tantalum stuff.
Paper.
Paper, yeah, paper with,
Okay.
and the paper is usually impregnated with wax or something like that to. Okay, back one, please. Charge plates far apart. Okay, this is capacitors in series. They show it in the old way like you do with resistors when you put the 2 above and the 2 below, but the 2 above are multiplied and 2 below are added. That is, if you remember in mathematics, you have a denominator and a numerator and denominator. Numerator's on top?
Yeah.
Okay, well the denominator's on top and the numerator's on the bottom here. Because this should be 1 over CE, and then it would be the other way around. So that's why you multiply the 2 in the top, bottom, and then add the 2 in the top. So if you have a 1/8 and 1/4, then it's did you put those 2 together? It's 24 and 2. This is 12. But you can do the long form if you want. Okay, next one. In parallel, the surface area of the plates add up to be greater. This makes the total capacitance higher. And this makes sense. When you're in parallel, boy, I can store electricity here, and I can store electricity here. So double the electricity, right? If they're the same size. So you just add them together. It's the complete opposite of resistors and inductors. That's basically what you need to remember. Next, please. Okay, now we're into inductance. Inductive reactance, I mean. So, we talked about the current going through here and being slowed down and having trouble. So there is a way to measure the amount of resistance in the coil, and it's called reactance. It's reactance because it's unlike resistance. There's no loss, there's no energy loss, but it is something that will change the value of the circuit. Inductive reactance is X with a little L on it. Okay? It equals 2 pi frequency times the henries. These have to be in henries, these have to be in cycles per second. So remember we said we had millihenries and microhenries, so you have to make sure that you get the decimal point in the right place to multiply that out to get your inductive reactance. Because inductive reactance is the resistance to alternating current flow in an inductor. Any questions?
This one's over my head.
It's over your head?
Well, at least if I'm alone, I'll.
No,
stay
no, there's
alone.
no, that, that means I'm not explaining it right.
I second that.
Okay.
Okay.
You want me to try?
No, it's okay. I mean, this is a hard concept to understand. When I told you that voltage, or the current lags the voltage, it does. And that, there's a measurement for that, and it's called reactance. And that reactance is the resistance that that coil creates for the electricity trying to go through it and back and forth, right? And that resistance we call reactance because it's something that reacts to change, okay? And that change is the frequency of the signal or the current.
So 2 pi FL means frequency?
2 times pi is just pi.
Right.
3.14159, whatever.
Yeah.
Frequency is the frequency of the applied voltage. Okay, and like our lights are 60 cycle.
Yeah.
In radio, we use frequencies up into the gigahertz. Okay, so the change if you change the frequency, you're going to increase the reactance. If you get more frequency, if you have more henries, you're going to increase the reactance. Okay, and that reactance figure is important, and it'll become clearer as we go.
So in order to increase the henries in the circuit, you would increase the inductance of the inductor there by
Well, you would change the inductor because, or you can,
by either adding coils.
I can change the inductance of this coil by clipping out here, clipping out there, or clipping out there. So my input is here, my output is here,
Oh, okay.
or my output is there. You change the number of turns.
Or you can
number
add
of
more
turns.
rotations.
Yeah, you can
Yeah.
more, or you can change the coil.
Okay.
What do you call that thing? The core. Okay, to increase the inductance of the coil.
Now what's X again?
X is reactance. And this is inductive reactance. I think it, give me the next one, it's probably on the, no, it's not, so I'll write it on the board for you. You all know me now, I don't need that anymore.
So L is inductives, X is reactives, or
Reactance.
reactants.
Okay? And remember, these words describe things, eh? Inductive means it has to do with an inductor. Reactance means it's something that is reacting. Okay, we're reacting to the change in voltage, the change in current.
So XL is the short form for,
Inductive reactance. Okay, now show me the next one. I'm going to zip through this and then it'll become clear.
okay.
This is a capacitor. Capacitor has capacitance, but it also has capacitive reactance. I neglected to tell you, in a capacitor, the current leads the voltage. And this is very important. So when you first, if you put DC on a capacitor, it's like a dead short. Zoom, that current goes in there. Okay, so it's ahead of the, when you do the AC part, it's ahead of the voltage.
In what case is voltage leading current?
In
Reactance.
Reactance.
No, inductive.
Inductive.
Inductor.
Voltage leads the current, but like I told you, always current lags the voltage, current leads the voltage. Always think in terms of current because voltage doesn't go anywhere. Voltage is a pressure. Okay, it doesn't move. The only thing that moves in a circuit is current. And in the AC circuit, that current is flying back and forth, okay, like a pendulum.
Voltage is a drop of water, river is the current, like the flow.
Okay, in water terms, voltage is the head,
Okay.
current is the flow.
Okay.
Okay, so you have a big dam and it has all this water behind it.
Yeah.
That's the voltage,
Okay.
the pressure. Okay, Okay.
We learned that before. Okay.
Well, not to repeat it. Okay.
No, that's good. It's good. I needed you to repeat it. So
Yeah, no problem. We're all friends here. Capacitive reactance is the exact opposite. So if I increase the frequency, I'm going to decrease the capacitive reactance. If I increase the capacitance, I'm going to decrease the capacitive reactance. Because it's an inverse ratio, an inverse equation. Okay? So the capacitive reactance is the 1 over 2 pi frequency capacitance. So the two formulas both have to do with frequency. They both have to do with, one has to do with inductance, sorry, not both. One has to do with inductance, the other has to do with capacitance. And that's the resistance to the movement of the frequency of the current.
I was just looking for how do you spell a farad.
Farad, F-A-R-A-D. That's named after a guy, Faraday.
Need a cage.
Who knows the name of the fellow who made AC popular?
Nikola Tesla?
Yeah. Do you know where there's a statue of Nikola Tesla?
No.
Niagara Falls. Why is there a statue there? He built the first alternating current generator at Niagara Falls. Piece of information. Nikola Tesla is a very interesting guy. He's the guy who told us about inductance, about inducing a current with using a magnetic field. Okay? Try the next one, please. If a circuit contains both resistance and reactance, the opposition to AC current is called impedance. Oh, I hate this one. So impedance is even harder to understand. The symbol for impedance is Z, or Z if you're an American, and measured in ohms. For a series circuit, the formula for resonance is, that's resonance. But we got to get there first. Okay, if we put an inductor and a capacitor in series, now we have inductive reactance, capacitive reactance. Something's going to happen, right? And the thing that can happen is that we can get to a point where it looks like there's nothing there. That's called resonance. Because one is slowing the current, one is speeding the current. So they're going to equal out.
They're in neutral each other.
Yeah. The other thing we can do is we can put them in parallel. A capacitor on this side and a resistor and a inductor on this side. Now we've got this thing going on. We have only one frequency will go through there, right? It's called filtering. And
So you're controlling the frequency by adding them in.
you're not changing the frequency, you're changing the reactance, the resistance. We'll get there, don't worry. Give me the next one. I don't like the way this is set up. Resonance is the situation where the inductive reactance is equal to the capacitive reactance. Formula for resonance is all units are expressed in basic units. So I'm not sure what FR is in this formula. Anyway, 1 over 2 pi square root of LC. So the frequency of resonance, frequency I would think. Give me the next one, please.
Oh, 1 second, I'm just jotting this down.
Don't worry about this.
Okay.
It's going to come back. There's the series one. Series circuit has minimum impedance at resonance. Okay, next one. Maximum impedance at resonance. Okay. Okay, next one. So these are not, okay, those, we aren't there yet. I'll have to go from here. And we'll go back to well, 3 or 4 of those back. Because there's more stuff I want to talk about. We did the number of turns and all that. But before we, and then we did capacitor. I'm sorry, it's my first time doing this course.
Oh, that's all right, we're all friends here.
Yep. Okay, so we talked about 2 pi FL, 2 pi 1 over 2 pi FC. How did we get to impedance from this stupid thing? Okay, well, I don't think we really fully understand reactance yet, do we?
I understand how they would become, they would neutral each other out, like,
Okay, that's good.
it's like yin and yang, right?
Pretty much.
Okay.
Resonance is out of frequency. I'm not really sure what they're trying to say here. And unfortunately, impedance is Z, and it's in ohms. Oh well. We talked about varying inductors, but we didn't talk about varying capacitors, did we? We didn't really talk about capacitors enough, I don't think. And I was following this, and it's not a good way to do it. A capacitor, you can change the capacitor in the same way with here. What they usually do is there's a roller goes along here, okay, for the change, and that roller is your output. This is your input, and this is your output. This is not connected. So that roller will determine your inductance, okay?
As it touches each coil, it
Yeah, it changes.
determines
How many turns are in the coil?
They,
Okay.
they don't touch the coil around.
Eh?
They don't touch the capacitor plates.
No, this is inductor.
Oh, because you mentioned capacitors.
Well, I'm going to get to the capacitor now. The capacitor has plates. You imagine my fingers as plates, and we move them in and out. We can change the capacitance because more plate is in relation to the other plate. Okay, so those are in older radios. That's how we tuned them, was with that capacitor. Nowadays, it's all done by a little bit different technology. It's done by electronics, and we don't use that except in antenna tuners and high current amplifiers. And the big amplifiers, you need a big tuner for them, because remember, this is where impedance comes in, because you have to impedance match your antenna to your radio or to your output. So the impedances have to be the same so that they can pass the maximum amount of current. If they're not the same, then you have losses and
That's where you get
damage.
the noise and the stuff from the interference.
No, that's a different issue.
Okay.
So if I don't match my impedance, then I cannot make maximum transfer of energy. And that's what's important. That's what's always important. You want maximum transfer of energy. And that's where this resonance stuff comes in too, eh? So, but if your impedance are matched, then it's like a zero resonance. Through we go.
Can I give us just, you guys are into stereos? If you look at a stereo, your output out of a stereo is usually what 8 ohm speaker, 5 ohm speaker. If you have an 8 ohm output on a stereo system, that's impedance.
Yeah.
Okay. Your speaker has to be also 8 ohms. If you were to put 5 ohm speakers on an 8 ohm radio, you would blow your speaker up because they're not impedance matched. You're not allowing that maximum transfer. Okay, does that make sense? And that's what he's trying to, what Ron is trying to say. That
But trying to explain impedance
it's
is hard.
really difficult.
Impedance is really hard to understand because of these formulae. But inductance and capacitance, they're fairly straightforward. Inductance is the storing of a magnetic field, and capacitance is the storing of electrical charge. So just remember that. Anyway, when a circuit contains both resistance and reactance, the opposition to the flow of AC circuit in the circuit is called impedance, and it's measured in ohms. The symbol for impedance is capital letter Z. When AC flows in any circuit containing resistance and reactance, then one must assume that the circuit will have some value of impedance that is greater than simply the resistance. Okay, so if we have impedance, we know is this formula for with inductance and capacitance, inductive reactance and inductive capacitance, or inductive reactance and capacitive reactance. And then you add resistance, because there's resistance in everything. There's resistance in this coil as well as the reactance in the coil. Okay, wire has resistance. All of those things have to be added together, and that's what gives you your impedance. The more resistance you have, the higher your impedance. The more capacitance and the more reactance, the higher your impedance. But we have to understand resonance, and I'm not really sure how I'm going to get there yet.
Well, Ron, will you take a break at 8?
Okay, yeah, give me a break, and I got kind of lost. We'll take a break.